Assalamualaikum. My name is Iqmalfitri with my groupmate Nileish, Aiman, Divaneshwaran, and also Amar. And today we will be presenting about CFD analysis of flow and heat exchanger in fin and tube. So for the background of the project, we study the heat exchanger that is widely used in power generation, vehicle, HVAC, and chemical industry. It consists of the extended fin on the surface area, and due to its limitation because it is expensive, so to make the full analysis, we need to do the ANSYS simulation. So for the objective, first we will simulate the flow and heat transfer for the heat exchanger in fin and tube using ANSYS Workbench, and we will visualize the airflow and temperature around the heat exchanger, and lastly we analyze the heat transfer coefficient and also pressure drop in multiple variables.
Good day everyone, my name is Divaneshwaran, son of Yanesagar, and my metric number is MA22021. Now I am going to explain about scope of study. This project uses 2D simulation and ANSYS Fluent to analyze airflow in fin and tube heat exchangers. The working fluid is air at 27 degrees Celsius and the inner wall of the tube is maintained at 100 degrees Celsius. We studied two tube arrangements in line and staggered with inlet velocity ranging from 1.8 to 3.8 meter per second and tube diameters from 6.35 mm to 15 mm. A mesh independence test with 5 mesh sizes ensures accuracy. Finally, experimental and CFD results are compared and the difference is kept below 10%. Here is the problem description. This study focuses on CFD analysis of airflow through a fin and tube heat exchangers under steady state incompressible conditions. We evaluate two setups by side tube with fins and opposite tubes with fins. Symmetry reduces computational cost and flow is stabilized by extending the domain under 80 mm downstream. Moreover, here's the mathematical formulation and equations. We use the continuity, momentum, and energy equation to model airflow. Key values include heat transfer coefficients, pressure drop, and mean temperature. The outlet temperature is obtained from simulation and used in the temperature difference calculations.
Assalamualaikum warahmatullahi wabarakatuh. So next is our geometry creation and name selection. So we designed our model in Automotive Inventor 2025. The left side is the inline surface design and right side is the staggered surface design of the exchanger. So next, this is the computational domain for the heat exchanger. As we can see, the above and the below, which are inline and staggered configuration. So we save the file as step files in the Autodesk Inventor for 2025. So the steps for to open the design is we click on geometry, import geometry, and choose the step file that we have saved before. Next, we create the name selection for the design. First is the inlet, second is the outlet, next is the wall, tube, upper sky, and lower sky. These are denominated by A, B, C, D, E, and F, as shown in the figure. So next, we have the mesh selection and the justification for the selection. So we have chosen the mesh size of 0.01 mm until 0.002 mm. This is because it has a skewness of less than 0.9, orthogonal quality more than 0.2, and aspect ratio is less than 5.
We use CNT-Resin Composite for the fins because it's lightweight and resists corrosion. It has a density of 1,230 kg per meter cube, thermal conductivity of 2.5 watt per meter Kelvin, and heat capacity of 1100 joule per kilogram Kelvin. These properties make it good alternative to copper, especially for reducing weight without sacrificing too much thermal performance. Here's a quick comparison of all materials used. Air is the working fluid. Aluminium was used for the tubes. For the fins, copper had the highest thermal conductivity but is much heavier. CNT-Resin, although lower in conductivity, is lighter and still performs well. This balance is key in optimizing heat exchanger design. We set the inlet at velocity between 1.8 and 3.8 meter per second at 27 degrees Celsius and the outlet at atmospheric pressure. All walls were heated at a constant 100 degrees Celsius. Symmetry was applied to reduce the computational domain and keep the simulation efficient realistic.
Okay, so now we have the settings for the simulation procedure. So we have the steady state and pressure based solver, the standard K epsilon model with scalable wall functions for the turbulence model. Then we have the second order obtained for momentum and energy discretization, and the simple scheme, and followed by the hybrid initialization. Okay, so next would be the mesh independence analysis. So for the first mesh size, we have 0.01 meters. This shows the mean trends, but then it varies a lot in temperature at higher positions. Next, we have 0.08 meters, which is a better precision than 0.01. But then the low power, which is designed for intermediate level and leads to better convergence. Then we have the 0.006 meters. This combines details with performing tasks and ideal for production use. Then followed by 0.04 meters and also 0.02 meters, which is the most precise results. Okay, so these are the various operating parameters, and the parameters are effect of inlet velocity, effect of tube arrangement, effect of fin material, and effect of tube diameters. So as you can see here, these are all the informations and details for each of those parameters.
And here we see the velocity contour and also the vector comparison between the inline arrangement and staggered arrangement. As we can see here, the arrangement also affect how the flow between each of the fin. And next, we can also see the temperature contour between inline arrangement and also staggered arrangement. As we can see, it bring a little bit of difference between each arrangement. Here we can see how each parameter affect the temperature. For the first one, the higher the inlet velocity is, the lower the temperature will be at the end of the fin. Next, the inline tube arrangement have higher temperature at the end of the fin compared to the staggered tube arrangement. Next, for the fin material, copper have higher temperature compared to the CNT resin. And lastly, for the effect of tube diameter, the bigger the tube diameter, the bigger the temperature will be at the end of the fin.
Therefore, velocity analysis for HTC and pressure drop. Here, we analyze the effect of velocity on heat transfer coefficient and pressure drop. From the graph, we can see that as velocity increases, the HTC decreases, while the pressure drop increases. This trade-off is crucial in selecting the optimal velocity for efficiency in heat exchangers.
So next is the tube diameter analysis for heat transfer coefficient and pressure drop. We can see as the tube is getting bigger, the pressure and the heat transfer coefficient is going up, with a slight difference of the pressure being going down a bit before going up.
This slide compares inline and staggered tube layouts. The staggered arrangement produces a higher heat transfer coefficient due to better airflow mixing. However, it also causes a higher pressure drop, which means more energy is needed to push air through. So it's a trade-off between performance and system efficiency.
Okay, so this is the fin material analysis for the heat transfer coefficient and also the pressure drop. So as you can see here, for the fin material, the copper is way higher than CNT resin in terms of heat transfer coefficient, and for the pressure drop, you can see here that the CNT resin has also quite a high amount of value compared to copper for pressure drop. So both of them are quite opposite in values. Okay, so in conclusion, we can conclude that the study achieved its objectives by evaluating how design parameters such as the tube layout, velocity, and material affects performance. And also for future improvements, we can expand to 3D simulations using advanced turbulence models, and also introducing transient analysis, which is recommended to enhance accuracy and also realism in future heat exchangers design. So that's it from us. Thank you.